Okay, so we'll continue on here. And okay, so on Monday we were talking Monte Carlo integration, and we will continue in Monte Carlo integration. And we said if we've got some integral I, which is going to be the integral from a to b of some function h of x dx, this can be approximated, okay, by saying I hat is going to be equal to the interval b minus a times h bar sub n, the Monte Carlo estimate of this thing, which is b minus a, and an h bar of n is going to be 1 over n times the sample mean from I equals 1 to n of h of xi's, where x is drawn from the uniform from A to B, okay? So this is what we did on Monday, right? Because well, I guess earlier we said I can be equal to b minus a times the expected value of h of x, expected value over f, where f is the integral there. Okay. Okay, so this is good. This is what we did on Monday, right? All right, and I think on Monday we had kind of we had this funny looking curve, and it was like, well, whatever, you know, I don't, whatever, something like this, right? And then basically the idea was, hang on, we just randomly just sample points along this thing at, you know, random locations, and we take the we just average their values, okay? And then you know, just continue sampling points, and then we average their values to get our estimate h bar sub n. Keep sampling points. X sub I coming from basically the uniform on A to B, and then we just take the plug in, calculate h of x sub I, and then we take the sample mean of all of those things. Okay, and we studied properties. So that was Monday, and this is this is fine. This is a decent method for approximating an integral. One issue, though, is that it requires you to have a closed interval. Okay, you can only do it on a closed space, and if the interval itself, if well, we'll take a look, but basically if you have an open interval, this is not going to work, because you can't go from if one of these things is infinite, it's not possible to draw uniform samples on an infinite interval. So what can we do next? All right, so let's take a look. Here, wait, let me just kind of recap, is that the expected value of f on some, of some function h of x is equal to the integral of that function h of x times f of x dx over kind of the space D, okay, where D is the support of x, okay? Meaning that x comes from some, x is defined, x is a random variable defined by the PDF f. Okay, so if d is the support of x, you know, the expected value of this function over the over f, over the kind of the probability distribution f is this thing, okay? And and we said we can approximate this, okay? The expected value of f of h of x can be approximated by our Monte Carlo estimate, which is going to be equal to 1 over n of the sum of h of x sub I, where we draw where x's sub i's come from, basically are drawn from whatever this is. Okay, and this worked for the uniform case because the uniform case was just a constant. Okay, well, we could have other functions. Okay, we can have another integral that maybe can be rewritten as in the form of a PDF of a different random variable. So not a uniform random variable, but a different kind of random variable. Okay, so you know, let's just say, what if we wanted to sample, to calculate over an indefinite interval. Okay, like e.g. from 0 to infinity, or minus infinity to infinity, or something like that. Okay. All right. If we can get the interval written in the form related to some probability function, then we can use this strategy. Okay, so perhaps we can rewrite our integral you know, as a product of a probability density f of x and some function h of x. Okay, so we might be able to rewrite our integral as a product of a probability density and some function h of x. Okay, and then we can just follow the same strategy from before. Yes? So I guess, yeah, it'd be integral of a, like, some other function here. Okay, so yeah, rewrite our integral. The integral, whatever it is, if you can rewrite it into a product of a probability density and a function, then you can estimate kind of the, you know, whatever it is that we're going for by using Monte Carlo estimation. Okay. All right, so let me do kind of a, you know, a little example here. Or here, let me just kind of okay. All right, so let's say just an example, okay? All right, what is the normal CDF, okay? The normal CDF is defined as, we can say, this is capital big F of x is equal to the probability that z is less than or equal to some value x okay, and we define this integral as going from negative infinity to x of the basically the normal PDF. So it's going to be 1 over root 2 pi e to the negative t squared over 2 dt. Okay, so that we can keep this in terms of x. All right, so the normal CDF has no closed form expression. Okay, and this will be a good candidate to use for Monte Carlo estimation. Okay, so what we're going to do is we're going to let f of x be kind of our normal PDF. Okay, so we will use okay. All right, so basically we want to rewrite this integral, negative infinity to x of basically 1 over 2 pi e to the negative t squared over 2 dt into some form of basically the integral over the entire space D of h of x and f of x dx, okay? Where x is drawn from f of x and d is the kind of support of x. So we want to get this thing into this form here. And if we do this, if we can get this integral in this form, if we can achieve that, we can estimate the original integral with our Monte Carlo estimator, h bar sub n. Okay, so what can we do to get our thing kind of in this form? Okay, so the trick, the thing is here we're going from negative infinity to x. What is the support of x here? Well, actually, here, let me say, all right, so we got, so this is our original integral. So sorry, I'm just, you don't have to rewrite all of this because I'm just getting it so it fits on this screen. Okay, and we want it in this form, right? Okay, so I'm going to say let f of x be the normal PDF, which is going to be 1 over root 2 pi e to the negative x squared over 2, okay? All right, so here, and in this case, the support of x is negative infinity to infinity. All right, so now I've got from negative infinity to infinity, and we're gonna keep in some function h of x here, and then I'm gonna plug in this 1 over root 2 pi e to the negative x squared over 2 dx. All right. All right. So this is what we want. This is what I currently have. So what can I use for h of x to kind of make it equivalent to this? Any ideas? So, because these two things are pretty much the same, right? So this is basically saying x is going to come from basically a normal 0, 1, right? But I can't just plug in, take values of x, and integrate across from negative infinity to positive infinity, okay? So I need to do something so that it's equivalent to going from here. It's equivalent to saying our integral goes from negative infinity to x rather than from negative infinity to positive infinity. Okay, so what we're going to use, all right, so to get this to work, yeah, we will use an indicator function for h of x, okay? And what is that indicator function going to be? It's going to be the indicator if we're going to basically say if z is less than x, we'll let this equal to 1, and if it's greater than x, it'll be, so I probably should have used different letters here. Okay. Sorry, I'm going to switch things. Yeah, all right, okay, we'll just, so we'll say if z is less than or equal to x, here, our indicator function, z less than or equal to x, will be this, okay? So basically this is equal to 1 if z is less than or equal to x, and it's 0 if z is greater than x. And what we will have here now is that if we throw that in here, then kind of the expected value of this will work out here. Okay, so let me see. Can I write this in here? Okay. So basically, we can split this up into two parts: negative infinity to x of our indicator function, z less than or equal to x of basically, I should use a different letter here. 1 over 2 pi e to the negative x squared over 2 dx. Oh, let me throw in a t here. Sorry, I'm going to switch this up to t's here. Okay, and then and it goes from x to infinity of, and in this case we have z greater than x of 1 over root 2 pi e to the negative t squared over 2 dt, okay? And over here, this part for on this interval is 1, and on this interval it's 0, and so we end up getting exactly what we want, which is going to be negative infinity to x of 1 over root 2 pi e to the negative t squared over 2 dt. Okay, so this is what we want, and by using an indicator function of our h, we're in good shape here. Is this okay? All right, so you know, what we want is this original thing, okay? And we're trying to get it in the form h of x, f of x. And we just have to think of what our h of x needs to be in order to kind of make it equivalent to this part here. Okay, so now that we have that, then this is how we do Monte Carlo estimation, okay? Okay, so now we draw a bunch of x sub i's, or x super I, okay, x1, x2, all the way up to x sub n, coming iid from f of x. In this case, f of x is going to be standard normal. All right, and then we compute h of x okay, and then we estimate the expected value of f of this thing so this is exactly the same, it's just that we're not drawing from the uniform, but we're drawing from some other distribution f, okay? In this case. All right, so okay, so going back to the standard normal, standard normal CDF, okay, we're going to have f of x is equal to the probability that z is less than or equal to x, which can be written as the expected value of I being z less than or equal to x, okay? And so, you know, so our h of x is this indicator function, where z's are drawn IID from normal 0, 1. Okay, so basically what we'll do is generate z1, z2, etc., from normal 0, 1. Then we compute h applied to our standard normal, okay, which will be 1 if z is less than or equal to x, 0 if z is greater than x, and then we take the mean, take the sample mean of all those zeros and ones. Zeros and ones, okay? And so our estimate of the normal CDF is going to be h bar of n, which is 1 over n times basically this indicator function. All right, and that makes sense, right? So if we're thinking of the normal CDF, we're just, and we say, you know, what's the cumulative probability that z is less than you know, something like 3 or something like that, then we just randomly sample values from the standard normal, and we say what proportion of our values are less than 3, and it's going to be like 99 point something %, and that's going to be our estimate of the CDF. Okay. So here's a method for kind of you know, getting what we need by Monte Carlo integration here. This is okay? Okay, then there's this related topic, and we'll get started, and we probably won't get to finish today. I don't know, maybe we'll get through it. Called importance sampling. Okay, so importance sampling, I don't know why we call it importance sampling, to be honest. It should be like weighted Monte Carlo integration or something like that, okay? It's called importance sampling, but, you know, in my opinion, not a good name. Probably something like weighted Monte Carlo integration is probably better. Because importance sampling makes it sound like we're doing like random sampling or something, in my opinion. Okay, but whatever. All right, it's Monte Carlo integration, but it's a little bit different. Okay, so what we just saw was okay, so regular Monte Carlo integration. What we do is we estimate e of f of x of some function h of x, you know, is equal to this thing. Okay, but this requires that we can sample from f of x, okay? We can sample from f of x directly. Okay, and so, you know, kind of in our two examples, you know, f of x has been some kind of constant if we're sampling from the random uniform, or f of x was the normal PDF, and we can sample from the normal distribution directly. Okay, but we might have some function f of x, and we are unable to sample from it directly. Okay, so, you know, so I'll just write, so far, f of x was either a constant, like 1 over b minus a, okay, and we sample from the uniform, or, you know, f of x was a PDF of a known random variable, like the normal distribution. Okay. We could end up in a situation where, you know, maybe you refactor it into something, but you cannot sample from f of x directly, okay? What do we do? Directly. Okay. Maybe I should just pause and just make sure I'm not going too quickly here. Oh, did everybody respond to the online poll? We said option choice C. Everybody got that? Okay. You get like 1 minute warning. This is like, I'm being too generous with this. Whatever. All right. Okay, what do we do if we cannot sample from f of x directly? Okay, well, we have an alternate thing that we can do, and this is going to be, this is called importance sampling, okay? And it's a little bit like rejection sampling, but it's different, okay? All right. Okay, I'm going to close down the poll here. 82. Are there 82 of you here? I don't know. Okay, I'll think about this. All right, maybe I'll call some names here. Okay, instead of sampling from f of x, because we can't sample it directly, all right, so this is importance sampling, okay, so we want, what we want is this thing. Okay, so it's the expected value of this function if our x's come from some distribution x, right? So just a reminder, it's the expected value of h of x if x comes from some distribution defined by f of x, okay? We want this, but we cannot sample from f of x directly. Okay, so this is what we do. Instead, we sample from a different distribution. All right, we just say, all right, instead we will sample from a different distribution. We say, okay, well, I don't know how to sample from f of x. All right, so I'm going to sample from g of x instead. Okay. All right, we called the g of x our candidate distribution. G of x is called the candidate or trial distribution. Okay. And the only requirement is that g of x has the same support as f of x, okay? So, or I should say the support of g of x contains the support of f of x. So the support of g of x can be bigger than the support of f of x, but it can't be smaller, all right? So the only requirement, okay, so the requirement for g of x is that its support contains the support of f of x. So, okay. So all we're going to do is we're going to just sample instead from g of x. But if we do that, okay, then we're not going to get the expected value of h of x if x is drawn from f of x. We're going to get the expected value of h of x if x is drawn from g of x. So what do? We kind of weight the values that we draw, okay? And so in order to get back the expected value of f of x, the expected value of h of x, where x is drawn from f, instead we're going to calculate this as the d of h of x of f of x divided by g of x times g of x dx, okay? So basically, I'm just multiplying this by 1, okay? Right? So I'm going to multiply it by g of x over g of x, right? But I'm going to factor it into kind of this, all right? And so this becomes so if you look at this, it's in the same form as this, except now I've got, this is the PDF part and this is the function part. And so this becomes, it's going to be the expected value if of g of basically h of x times f of x over g of x. Is that okay? So it's we're in this form of, we have some function times a PDF, right? Except now my PDF is going to be g of x, and the function is in this form, h of x times f of x over g of x. And so if I cannot sample from f directly, I will just sample from g instead, and now I have what I want, the expected value of h of x, and basically I just take my values and I just weigh them between the ratio of the PDF of f of x and the PDF of g of x. All right. So maybe we'll just do a little bit of intuition here, and then we'll do an example on Friday or something. Okay. So the idea here So again, we have this is h of x, and then we want this, but I'm going to divide by g of x and multiply by g of x dx, and this becomes the expected value over the function g of h of x f of x over g of x. Okay, so maybe, you know, I'm just making something up here. Okay. Okay, so maybe this is our this is the PDF of f of x. Okay. And instead, I'm going to this is a terrible picture here. Why am I having such a hard time here? Okay, and this up here is going to be the PDF of g of x, okay? And just for simplicity, let's say, let's just, for ease, let h of x be equal to 1, okay? And so effectively, we're just trying to calculate, you know, what's the mean of this thing, okay? We want to know what's the mean of this the black PDF here for f of x, okay? And what we're going to do is we're instead going to draw values from the blue PDF, g of x, okay? And so I'm not able to sample directly from f of x, but instead I sample from g of x. What this means is that in certain locations, like right here, I will sample my x at the correct ratio, okay? But over here, I'm going to sample too many values of x because my g of x is taller than the PDF of f of x. And so here, I sample too many values of x. Okay, and over here, I'm sampling I sample too few values of x. Okay. But what we have here, my ratio, f of x divided by g of x, is going to be less than 1. Okay? So the values that get sampled here get weighed less. Okay? And maybe I'll use a different color over here. And over here, where my g of x is shorter than f of x, okay, so here, you know, I sample too few values of x, but here f of x divided by g of x will be greater than 1, okay? And so by weighing the function, the value of the function by the proportion or the ratio between f of x and g of x, this corrects for the fact that I'm sampling too many values in one region and too few values in another region. Okay, so basically we have an importance weight f of x divided by g of x that corrects for our over or under sampling. Under sampling of values of x. I don't know. Do you guys want a roll call? We got 5 minutes left, but all right. Okay, we'll let it go. All right. All right. Are there any questions on this? Okay, so we'll look at I guess an example on Friday. Let's see. So I'm writing up the midterm, and I'm trying to figure out exactly what to include. I guess I'll talk a little bit more about this. I will say up to stuff I covered on Monday is fair game for the midterm. So today's stuff and Friday's stuff won't be on the midterm, but up through third week Monday, we'll say is fair game for the midterm exam, and that will be on this coming Monday, and I guess I'll detail out the midterm a little bit more on Friday. Is that all right? Okay, we will end here for today then, and we'll take a look at importance sampling in a little bit greater depth, and we'll end there. Okay.